Good evening. I'm here to work through the process of transforming a matrix into reduced row echelon form, a method that allows you to solve fairly large linear systems or systems of linear equations, just like what I have demonstrated or what I have here on the screen, using matrix techniques. So basically that's what I'm here to do, is to kind of talk you through the process. I'm going to talk through the idea behind it and what's happening first, just to give you a little bit of context. Then I'm going to go through and actually demonstrate it by showing you and writing out the moves that we're going to make, like the actual row operations, I guess we'll call them that. And then I'll do a fuller example at the end that works through it at a little bit more of a reasonable pace. Hopefully this is helpful. Sorry it's taken a little bit longer, but I figure, evergreen resource that can be used in the future potentially. So to start with, reduced row echelon form, it's a name to describe what we want our matrix to look like at the very end, that in such a way that will allow us to immediately solve the system that is represented by the original matrix. So to kind of get us into that, I think it's helpful to start by just sort of pointing out where these matrices come from. And I'm choosing a 2x2 example just for simplicity to sort of illustrate the idea before we actually go in and I show you how to actually execute and transform the matrix into reduced row echelon form. So starting with, there is a 2x2 system, two equations with two unknowns. There should be a solution if one exists. And of course, we have lots of methods to execute this and to try to solve for x and y. We could use elimination, we could use substitution. Heck, we could even just graph the two linear functions on the same xy plane, and assuming that they turn out nicely, we could solve for their intersection. Having said that, there is a fourth way, and that fourth way involves matrices. What we're going to do is we're going to transform this system of linear equations into a matrix, or specifically an augmented matrix, and then we're going to execute row operations to slowly whittle it down until we reach a particular form. So, and that form will be reduced row echelon form. So to give you an idea first, where we're at is, more than anything, like this can be represented as a matrix. So this would be the matrix, or at least the left-hand side of the equations, would be 2, -3, and 1, 4. So those represent the coefficients of x and y respectively. And basically from here, I'll go this way, like what the heck. Like I said, this is sort of off the cuff, so I haven't gotten a chance to plan it out, just sort of written the examples. So basically what we've got is the system on the left-hand side is completely equivalent to this matrix equation. It's basically, as you can see, the product of the 2x2 matrix 2, -3, 1, 4, and the 2 vector xy. And that product will be equal to 9, -1. And of course, if you know how to multiply matrices, which I'm pretty sure comes before reduced row echelon form in most linear algebra courses, as well as in pre-cal, if who's watching this, you know how to multiply this out, and you'll see that this actually ends up being a single, on the left side at least, it ends up being the single vector, by the way, 2x minus 3y, x plus 4y, like literally where we end up with, or what we end up with is this. So in other words, it's the exact same system that we started with. So we're just representing it in matrix form. Now in order to solve this though, we are going to transform this into what's called an augmented matrix. An augmented matrix is perfectly set up to transform in the way that we want to here. And what we do is we basically take that 2x2, 2, -3, 1, 4, and then we augment it by adding the constants on the right side. So in other words, this matrix, which is a 2x3 matrix, technically an augmented matrix, will allow us to transform it into this new form called reduced row echelon form. And what that's going to look like is 1, 0, 0, 1, or otherwise known as the 2x2 identity matrix on the left side. And then over on the right side, we'll end up with two numbers. Now those two numbers, like whatever they turn out to be, are going to be our x-coordinate and our y-coordinate. And if you're wondering why this works, and I guess it's easier if I actually give you a number. Let's go 42 and 37 as our number. Let's say those were the solutions. They're not, don't get excited, but if they were, what this equation or what this matrix would transform into is saying 1x plus 0y equals 42 and 0x plus 1y equals 37. And if you clean those up a little bit, you'll see the first one just says x equals 42 and the second one says y equals 37. So the idea here, other than the fact that I can't draw threes right now, the idea is that we turn it into a form that trivially solves our system of equations. So that's our goal. That's what we're trying to do. I'm going to eliminate that just for the sake of space. But basically that's what we want to do, is we want to transform our matrix, our augmented matrix, into this reduced row echelon form that trivially solves our system. And so that's what we're going to do. We just have to figure out moves that we can make that will allow this to happen, to transform it. So that's what I want to demonstrate here. So I want to show you a number of those techniques. And I think across my 2 examples, I've got all the techniques, but I may miss something because, again, like I said, this is off the cuff. So to start with, before we do anything else, since our ultimate goal here is a matrix system that looks like this one, I make it my absolute goal, first and foremost, to end up with a 1 in the upper left-hand corner before I do anything else. And now when I say that, there are 2 ways you could do this. We have a 2 up there right now. We could multiply the entire first row by 1/2. And in fact, if I was going to write that, I would say 1/2 R1 goes to R1. That would give us a new first row of 1, -3/2, and 9/2. So that's perfectly fine. That's a perfectly reasonable way to do that first step. But the presence of fractions doesn't scare me because I'm pretty good at fractions, but I just don't like it. It's just not as clean. So instead what I want to point out is that we can actually do a very simple operation to get a 1 up there, one that people don't usually even think of. I'm just going to swap rows 1 and rows 2. And so what that's going to do, what that equivalent to in the system is just literally switching the order of the equations. And I mean, who cares what order the equations are in? That works out just fine. So when we make this swap, that's going to make our new first row 1, 4, -1, and our second row 2, -3, and 9. So there's our new augmented matrix, and lo and behold, it has a 1 in that upper left-hand corner. We're good to go. Now that we have it though, our next move, like my next progression, is I want to proceed downward and get a 0 in every row below that upper left-hand corner 1. So unfortunately, because of the presence of that very 2, we don't have that. It wasn't set up for us perfectly. But we can handle that. We can take care of this. What I'm going to do is I'm going to take row 2, and I'm going to add to it -2 times row 1. And that result is going to become my new row 2. So basically, one of the things you can do when performing row operations is you can add multiples of the rows together. You can form, I think, linear combinations of the rows and replace a row with that linear combination. So in this case, that's what I'm going to do. I want to add -2 times R1 in order to transform this matrix a little bit. And the reason I've chosen -2 here is because, of course, we want to get rid of that 2, so I need to multiply 1 by -2 so that way it will zero out in the second row. So that's what I'm going to do. If I multiply -2 times the first row, I'm going to get -2, -8, and then -2, which is +2. And I'm going to add those to that second row. When I do, obviously my first row remains unchanged, but my second row will be 2 minus 2 is 0, -8 minus, or just -3 minus 8, which is -11, and 9 plus 2, which is 11. So there is our third setup. Still not quite there, but you can see it's getting closer for sure. So my next move from here, I'm looking at that bottom row. Like now that we've sort of gotten that one in place, my next move is to try to get that next, I believe they're called pivots. I'm pretty sure they're pivots. It's just been a little while for the jargon here. But basically I want to get a 1 right there. Right now I have this stinking -11. But what I'm going to do to fix that is I'm just noticing that since the second row has -11 and 11, I can just literally like divide the entire row by 11 and have it work out nicely. Or better yet, let's do -11 because that'll make that -11 turn into a +1. So that's what I'm going to do next. I'm going to take row 2, should do this properly. I'm going to multiply row 2 by -1 over 11, and I'm going to replace that original row 2 with our new row 2. So just so we can clean this one up here, again, our first row remains unchanged. We haven't touched it just yet. We will in a moment. But in our second row, we'll have 0 divided by -11, -11 divided by -11, and 11 divided by -11. That'll give me 0, 1, and -1. So interestingly enough, we have just solved part of our system. We now know y's value is going to be -1. But again, we're doing this to illustrate RREF, the reduced row echelon form, not solve the system really so much, so bear with me. So there we go. We're in good shape here. This is a great move. Like we are almost there. Only problem is, of course, my computer won't copy the correct thing. Only problem is I ran out of space on the right side, so let's bring this down a little bit. I'll make it a little larger too. So now what we need to do is we need to finally wrap this puppy up. Oops. We need to wrap this puppy up by now fixing it so the upper right-hand corner has zeros. So basically we're trying to make sure those columns, the pivot columns, have only the 1, 1 and all zeros everywhere else, so that the system is in fully reduced row echelon form, as opposed to just row echelon form, I think, as opposed to reduced. Maybe, again, jargon might be off. So in this case, what I want to do is I need to get rid of that 4. So what I'm going to do is I'm going to multiply the second row by -4 and then add it in there. So just like I did before, I'm going to take now row 1 and I'm going to add -4 times row 2 to it in order to create my new row 1. So that's a little bit of a mouthful. So here first, what I'm going to do is I'm going to copy down my second row, which is staying exactly the same. And then for my first row, I'm going to prepare to combine those together. So if I multiply this row by -4, then that's going to be 0 times -4 is 0. 1 times -4 is -4. And -1 times -4, which is +4. Now I'm going to add those together. So 1 plus 0 is 1. It's good. That shouldn't ever change because remember we got zeros everywhere else. So that way when we add linear combinations, they're not going to affect the 1 in the pivot spot. Then we have 4 minus 4, which is 0. That's also good. That was the entire point. We were trying to get this so that we had 1s and 0s, like the identity matrix. And then -1 plus 4 is going to be 3. And lo and behold, we have in fact just solved our system. This tells me that our solution point, our ordered pair, or our 2-vector, depending on how you want to think about it, is going to be the point 3, -1. And now I'm pretty confident because, again, I wrote that problem ahead of working on this, but let's say that you weren't confident. You could go back to our original system and check. 2 times 3 minus 3 times -1 is 6 plus 3, which is 9. That's good. And our second one is 3 plus 4 times -1. It's going to be 3 minus 4, which is -1, which matches as well. So we have successfully executed this. We transformed our matrix into reduced row echelon form. That's what's right here. This is the RREF, reduced row echelon form. It fits. It's the identity matrix augmented with the solution vector, basically. And we were able to find the solution to our system. So there is sort of your first basic example of reduced row echelon form being used to solve a system of linear equations. Okay, now having done one sort of limited academic example just to sort of illustrate the techniques and give you a little bit of the process itself sort of shown on a simple, clean system that we could solve other ways, I do want to do a fuller example here in closer to real time just so you can kind of see what it looks like and how I sort of proceed forward through it. So for this, again, I chose a 3x3 system. I have good techniques for solving 3x3 systems. I actually learned them from Miss Nakamura at Franklin when I first started teaching there. Really nice and organized. In fact, weirdly enough, it's one of the hottest videos ever of all time on my YouTube channel, weirdly enough. But beside the point, I wanted to do this using matrix operations, row operations, elementary row operations, so that we could demonstrate how transforming something into reduced row echelon form might actually work. Free up storage space. Oh no, I don't like when it says that. This could be a problem, but we're gonna go for it. We're gonna go for it. What are we gonna do? So in here, the first thing I want to do is I want to transform this into a matrix. But well, let's just transform it into a matrix first. We'll go with the classic style first. Let's just make this into a matrix. So going coefficient by coefficient, we'll have 5, 5, 5. Sounds like a Hollywood phone number. Then we'll have -2, 0. I'm including a 0 there because there's no y term in that second equation. So -2, 0, 3, and -8. And then 1, -4, -1, and -13. So now as I set up our augmented matrix, I do have to sort of inform you that I haven't tested this. I haven't done the full problem. I've just sort of written it out and made sure the solution works. So this could turn out to be really like gnarly on the inside, even though I did make it so all the solutions are integers. But what are you going to do? You get what you pay for, and I'm not being paid for this. So from here, let's actually start it off and just kind of start attacking this. And I'll tell you what, before I start to attack anything here, I see something that's really helpful. I want to get this into reduced row echelon form, which means we need to eventually get a matrix that looks like 1, 0, 0, 0, 1, 0, 0, 0, 1. So I need a 1 in that upper left-hand corner. And what I notice is that I have a 5. And in fact, I could go ahead and just multiply that first row by 1/5, and everything would come out really, really clean. So that's actually what I'm going to do first. I'm going to do 1/5 of R1, and then I'm going to replace that new version with that old version of R1 with this new R1. So when I do that, I'll pull it down here for a second. That's going to give me in my first row, since again we're just dividing everything by 5. That's going to give me the first row 1, 1, 1, 3. Then I'll have -2, 0, and 3. Oh, sorry, and -8. And then 1, -4, -1, and -13. So there is our new augmented matrix. Again, nothing's changed except we got that first row a little bit cleaner. Now from here, I've got a couple different moves that I need to make, and it might be helpful for us if I made this a little bigger so that we can actually set those things up. So you'll often, well, you won't often see because you won't see my work, but if you saw my work, you would see that I made these matrices pretty big so that I could write stuff with them. So as far as where we're at, this 1 is in perfect condition, or is perfect position, but I need to start getting rid of these other entries in that first pivot column. So I need to do a couple different things. The first thing I'm going to do is I'm going to take row 2, and I'm going to add 2 times row 1 into it to create a new version of row 2. So, and I'm going to make that pink just so we can see it really well. And in addition, I want to do the same thing with row 3. In this case, though, I'm going to take row 3, and then I'm going to add to it -1 times R1 in order to create a new R3. The thought process being, since we have a 1 here, if we multiply by -1 and then add those, we'll be able to get rid of that 1 in the lower left corner. So I'm going to do both of those at the same time. So first of all, I need to figure out what 2 times the first row will be, but that's going to be 2, 2, it's kind of easy this time, 2, and 6. So I'm going to be adding those numbers together. Again, this is just my personal way. You might have a more organized way. Maybe you can track stuff in your head. I just know this is my way of doing it. So when I combine all this together, by the way, I should be prepared for this. When I actually execute this, of course, 1, 1, 1, 3 is still our first row. But our second row is going to be 0, 2, 5, and -2. So that's from adding those numbers together. I'll repeat the same thing but with the third row. So we want to add -1 times the first row in this case. So that's going to be -1, -1, -1, and -3. When I combine all those together, 1 minus 1 is 0, -4 minus 1 is -5, -1 minus 1 is -2, and -13 minus 3 is -16. So there is our second version of the equation, and notice we've now got a completely fixed, like as a pitiful boxing, but we have a perfectly fixed first column. So everything's good to go on that first column. So now, unfortunately, in our next column, we've got a couple issues here to handle. Like basically, we're not going to be able to avoid the fractions, it doesn't look like. So we need to make sure that we are on top of this. So we have a couple different options here, but out of the ones that are there, I'm going to choose to work on the second row and try to transform this 2 into a 1. Now, of course, the presence of that 5 is going to complicate it a little bit, but there's just no way for us to fix. Excuse me, there's just no way for me to fix that. We're stuck with it. As I said, I didn't make sure every single operation was going to come out clean. So what I'm going to do from here is I'm going to multiply 1/2 times row 2, and I'm going to get that result and replace row 2 with it. So for the sake of simplicity here, and to save us a little bit of time, I'm going to go ahead and copy down my nice large version of this matrix, and I'm going to just go ahead and replace that row. So we had 0, 2, 5, and -2, so we are effectively dividing each of those by 2. You are allowed to multiply an entire equation through. When I do, I'm going to get 0, 1, that was good, we wanted the 1 there. 5 over 2, yeah, okay, we're not so thrilled about that one. And then -2 over 2, which is -1. So altogether, not the worst thing in the world to end up with a single fraction, but you know, it may not be your favorite thing in the world, but we've got to do what we got to do. So having done that though, now we're ready to start working. So in a sense, it's like we've executed this. Now we need to make sure that we get the 0 above it and below it, so that we have a perfect pivot column. So in doing that, we're going to have to think about operations here. Like first, moving up to the top, I'm going to take row 1 and I'm going to add to it -1 times row 2. That will create my new version of row 1. So why I'm doing that is I want to get rid of this 1 by subtracting 1, basically subtracting the second row. So when I do that, I'm going to have -0, -1, -5 over 2, and minus a -1 1. Sorry, I did that right there. See, look how easy it is to make an error. So easy to make an error here if we're not careful. So there we go. So we are adding -1 times that, and it looks like we have that ready. On the other hand, we also need to execute the bottom row. So the bottom row has that -5. So what I'm going to do for the bottom row is I'm going to take R3, and I'm going to add to it 5 times R2. And then I'll use that to replace my original R3. And again, if you're looking at this going, gosh, do you really do this every time? No, not really. I really don't write out the row operations normally. That's the only thing that I'm really changing here. I just want it to be clear what's happening, because otherwise I kind of go into autopilot mode with arithmetic and stuff. So hopefully it's helpful. So there we go. Okay, so now in executing these things, I guess before I go forward, I should go ahead and do the 5 times row 2. So that's going to be +0, +5, +25/2, oh joy, and then +-5. So actually I'm just going to write that as -5. I hope that's okay. So there we go. When I combine those together, I'm going to get 2 new versions of my first and third rows respectively. I'm going to have 1, 0. Now for this third entry, that's going to be 2/2 minus 5/2 is going to be -3/2. And then 3 plus 1 is 4. Down on my bottom row, being represented in red, we'll have 0. We'll have 0 again. Those are both good. This is all good stuff so far. Then we'll have -2 plus 25/2. That's -4/2. So that's going to end up being 21/2. And then finally, -21. Whew, boy. Yeah, it's not the funnest we've ever had, but it's still, I think, in good position. So we've done well here so far. We've done well. But what we do need to take care of now is we need to go ahead and get into this last little bit. And I'll tell you what, I'm seeing some issues here in that third row. I really want to get rid of those things. And more importantly, I need to get a 1 down there. So to do that, I'm just going to go ahead and straight up multiply by whatever it would take to transform this 21/2 into a 1. And specifically, that's going to be 2/21 times row 3 is going to become our new R3. And the good news there is it's actually going to work out really nicely, I think. I don't think we're going to have too much of a problem with this. So in doing so, of course, my first row and second row will stay the same. 1, 0, -3/2, and 4. And then that second row, which is 0, 1, 5/2, and -1. Down below on the bottom row, when I multiply by 2/21, we'll of course have 0, 0, 1. And now this is cool. 2/21 times -21 is going to be -2. Quick check in my answer key. Okay, cool. So, not my answer key, my solution. So far we've got the bottom row perfectly affixed. Everything looks really, really good here. So we're in good shape. And in fact, we're in good enough shape that I'm going to pull this down to the bottom and then frustratingly remove the little superfluous part I did not want. Okay. So there is our final, almost final version of the matrix. Now what we need to do is we need to start to attack those other 2 pieces in the pivot. This -3/2 and the 5/2. And I'm going to be real with you, they are not going to be the smoothest ones. We're going to have to do a little bit of fractioning. But that's okay, because that bottom row only has a little bit to work on. So the first thing I want to do is I want to attack that top row. So I need to get rid of a -3/2. So I'm going to do that by multiplying the bottom row, or row 3, by 3/2, and then adding that to row 1, and then replacing row 1 with it. So when I do that, that's going to be adding 0, 0, plus 3/2. And then down here on that bottom one, let's be careful. If I multiply -2 by positive 3/2, I'm going to get -3. So in other words, my new version of the first row is going to be 1, 0, 0, and 1. I know you can't normally check your answers like I can, but again, such are the vagaries of having written the problem. So there we go. We've got our first row done. And again, notice the fraction was a little annoying, but I don't know that I'd call it like difficult. It was just annoying, but it is what it is. And now I need one more color. I'm going to have to go in black because I have no other colors left here. So to get rid of the second row, we've got that 5/2. So I'm going to take -5/2 times the third row and add that to the second row in order to create my new version of the second row. So when I multiply that bottom row by 0, or by 5 over 2, excuse me, we'll have plus 0, minus 5 over 2. And now, once again, being careful, that's going to become positive 10 over 2, which is positive 5. And when I combine those together, I'm going to get 0, 1, and then 0, and positive 4. And what that does is it concludes our problem for us. It tells me that our solution to this system is a unique one. It's going to end up being x equals 1, y equals 4, and z equals negative 2. Unfortunately for us, that matches exactly what I had when I wrote out the problem ahead of writing this. So with that said, hopefully that was a helpful little overview. Like I said, it's just going to be a short little overview going through the process, showing you some of the row operations, explaining where it's coming from and what we're trying to do when we actually are executing or transforming a matrix into reduced row echelon form, and then giving you some familiarity both with like the row operations themselves, a notation that might be helpful to you if you're trying to track things, and then again being sort of practical. Like this is how I've always done the reduced row echelon form myself, so maybe it's helpful to you. In any event, like I said, I hope this was helpful. If it wasn't, well, it was just kind of off the cuff, and I was trying to create some sort of resource that might be useful. So, hope things are well. Have a good rest of your day.